I'd like to start our conversation about number theory, which is with a concept we've already considered in this course, and that concept is that of a divisor. Now, rather than trying to give a stuffy, formal-sounding proof, let's just remind ourselves of the idea of a divisor with lots of examples. We know that 3 is a divisor of 12 because 12 over 3 equals 4, and 4 is a whole number. Or we could say it a different way. When we divide 12 by 3, the remainder is 0. And that means 3 is a divisor of 12. In a similar manner, 5 is a divisor of 35, and 10 is a divisor of 100, and 6 is a divisor of 18. And if you think about it for a little bit, you'll notice that 1 is a divisor of every positive integer, including itself, because when you divide a number by 1, you get 0 as the remainder. Also, we can say that 5 is a factor of 35, and that 6 is a factor of 18. And so we're going to use the words divisor and factor somewhat interchangeably throughout this lesson. Now, in contrast, we know that 2 is not a divisor of 11, because when I divide 11 by 2, I get a remainder that's bigger than 0 in the process. And also, if I think of the fraction 11 over 2, I don't get a whole number after I try to simplify that. Also, 3 is not a divisor of 20 for the same reason, and 5 is not a divisor of 22. Now, this idea of a divisor is an extremely important one, and it's probably the most important idea in this lesson. From this idea of divisor, we can say lots of other things. Now, let's move to our second important idea in this lesson, and that's the idea of a prime number. Now, as I mentioned a few moments ago, 1 is a divisor of every positive number. It should also be clear that every number is a divisor of itself. In other words, 5 is a divisor of 5 because 5 over 5 equals 1, and that's a whole number. And 7 is a divisor of 7 for the same reason, and 23 is a divisor of 23. So what does this all mean? Well, one thing it means is that every number larger than 1 always has at least 2 divisors, namely 1 and the number itself. Of course, some numbers have lots more divisors than just 1 and the number itself. Take, for example, the number 12. It has many divisors, even though it isn't that large. The list of divisors for 12 is 1, 2, 3, 4, 6, and 12. But there are many other numbers out there which don't have so many divisors. In fact, they only have themselves and 1 as divisors in some cases. That's true, for example, of the number 5. The only divisors of 5 are 1 and 5. And the numbers 2, 3, and 4 are not divisors of 5. You can try to divide 5 by either 2 or 3 or 4, but you're going to find that they are not divisors of 5. And obviously, no number bigger than 5 is going to be a divisor of 5 either. And that leads us then to a very important definition, which is satisfied by the number 5 and lots of other numbers. Here is that definition. A number that is larger than 1 is called a prime number if the only divisors of that number are 1 and the number itself. Believe it or not, the prime numbers play an extremely important role in number theory, and so we're going to focus our attention on them for much of the rest of this lesson. Now, what are the prime numbers? Well, the list would begin something like 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and so on. They kind of jump around a bit. So it's a bit hard to see a pattern in this list. In fact, there's really no friendly pattern that has ever been found in the list of primes. But some very important things can be said about them, many of which Euclid himself saw centuries ago. First, Euclid proved that the list of prime numbers is infinite, which is a fancy way of saying that the list of prime numbers goes on forever and it never stops. You can never find something that you can call the largest prime because no such number exists. The prime numbers go on forever. Now that's pretty interesting, especially when you think about how you might try to prove that a list goes on forever if you don't have a nice formula or pattern for the list. Now if you're intrigued by that idea, I encourage you to continue your study of mathematics. Proofs of these kinds, like the fact that the number of primes is infinite, can really be cool to study if you continue on in your mathematics. Now, another thing we can say about the primes is that every number greater than 1 that we can think of can be factored into prime numbers. For example, you can write 10 as 2 times 5, and the 2 and the 5 are both primes. And you can write 12 as 2 times 2 times 3. But even more importantly, it's true that the way we write such a factorization is unique, as long as you don't worry about the order in which we write down the prime number factors. In other words, the only way to write 10 as a product of prime numbers is 2 times 5, or 5 times 2 if you're going to worry about the order you write them in. Oh, and in the case of a prime number, we just write down the number itself as its prime factorization. So we could write 7 as just 7, for example, and that would be the prime factorization of that number. Now, the fact that each number greater than 1 has such a prime factorization, and that that factorization is unique, has a special name. It's called the fundamental theorem of arithmetic. Now, that sounds pretty ominous and important, doesn't it? Well, don't be scared of the title. Let's just make sure we know what the fact is and learn to use it. I want us to pause in a moment and work out some of these prime factorizations for a few numbers, just to make sure that we can. Such a skill is going to be very, very important as we continue our study in number theory. But before we look at some of those examples, let me make a quick comment about the number 1, because lots of students ask this question: is the number 1 a prime number or not? Well, believe it or not, that question was asked and debated over and over for years. But the answer is easy. 1 is not a prime number. It is technically something we call a unit, but it is definitely not a prime. And if it were a prime, we'd really get annoyed really, really fast. Why? Well, because when we calculate the prime factorization of a number, like when I figured out that 10 equals 2 times 5, then we would also have to talk about 10 equaling 1 times 2 times 5 if 1 was a prime. Oh, but then we could write 10 as 1 to the 4th times 2 times 5, because 1 to the 4th is just 1. Oh, but then 10 could also be written as 1 to the 12th times 2 times 5, because 1 to the 12th is just 1 as well. And we could do this forever. And we would also have to constantly exclude 1 from lots of other conversations that we have about our mathematics. So to be honest, there are lots of reasons to not let 1 be prime. And one of those reasons is that it's very practical to push 1 out of the set of prime numbers. Okay, let's now work on finding some of these prime factorizations. The fundamental theorem of arithmetic tells me that I can find any such prime factorization for any number you give me. And it tells me that it's going to be unique. So let's do one such example now with the number 60. I want us to find the prime factorization of the number 60. Now, there are lots of different techniques for doing this kind of thing, but my preference is something called a factor tree. I think it's best because it keeps everything organized and it lets you see what is happening. The basic idea is to start factoring 60 until it has been whittled down to just prime factors. So we start by asking this question: what's one way to factor 60? Well, one way is to write it as 6 times 10. So, if we want to work with that, which we can, we start by writing a 60 on a piece of paper, and then we put 2 little diagonal line segments below the 60, one pointing downward left and the other pointing downward to the right. Then we put the 6 under one of those lines, and we put the 10 under the other. Now, what we've done is we've whittled the 60 into 2 pieces now, the 6 times the 10. And now we ask this question: can the 6 be factored some more? In other words, is the 6 prime or is it not prime? Well, 6 can be factored more. We can write it as 2 times 3. So under the 6, we draw 2 more little lines putting a 2 at the end of one of those lines and putting a 3 at the end of the other. Now, the 2 and the 3 are primes, so we can stop working on that part of the picture. In fact, I like to put a little circle around the 2 and a little circle around the 3 because they're primes. That way, I know I don't have to do anything else with that part of the picture. Now, we need to work on that 10 that's still there because the 10 is not prime. 10 can be factored as 2 times 5. So under the 10, we draw 2 more little line segments, putting a 2 at the end of one of the lines and a 5 at the end of the other. And the 2 and the 5 are primes. So if you're like me, you put a little circle around that 2 and a little circle around the 5 as well. Now, notice that at the bottom of each of the line pieces, the numbers are now circled. Every one of them are circled. And what does that mean? Once everything is circled in that way, we know we're done. That means we have the unique prime factorization for 60 completed. We can write 60 as 2 times 2 times 3 times 5. And that's because I have a 2 and another 2 and a 3 and a 5 circled in my factor tree. Now, by the way, I always like to write things from smallest to largest when I write down such a prime factorization. And that's why I wrote the factors the way I did, with the 2's first, then the 3, and then the 5. Also, it can be important to have things written as powers as often as you can. So I would note that you could also write 60 as 2 raised to the second power times 3 times 5. That's the same as 2 times 2 times 3 times 5. But what it has done now is consolidated those 2's into one power of 2. And that can be very helpful when you write down these prime factorizations. Now, lastly, we typically don't write down powers of 1. Notice I have a 3 there, and I didn't write an exponent above it. But I want you to realize that I could have written this prime factorization as 2 to the 2 times 3 to the 1 times 5 to the 1. That's actually what I meant when I wrote down 2 to the 2 times 3 times 5. So don't forget, when there's no exponent explicitly written, it means that that prime is being raised to the power of 1. Now, one last comment before we go to another example. It's very important that you notice that the factor tree we wrote earlier is not unique. There are other ways to write the factor tree. We could have started, for example, with the 60 on top, and then instead of splitting by 6 and 10, we could have split it as 2 times 30, and then we could have gone from there. So the trees themselves are not unique, but what is unique is the final outcome. Every factor tree that you write down for 60, no matter what you do in the middle in terms of the intermediate steps, you will always be left with 2 times 2 times 3 times 5 at the bottom of the tree. Or, if you want to write it with the exponential notation, 2 squared times 3 times 5. Okay, let's look at another example at this point. Let's find the prime factorization of the number 1,100. I'd like to suggest that you try this on your own first, drawing your own factor tree, and then let's come back together and see how you did. All right, I'm going to start this factor tree myself by writing down my 1100, and I know that 1100 or 1100 is the same as 11 times 100. So we could start our tree by drawing the 2 little lines underneath 1100, putting 11 on one side and 100 on the other. I would circle the 11 at this point because I know it's prime, and so nothing else needs to be done with that side of the factor tree. And now we focus on the 100. Well, that's the same as 50 times 2. So I write my 2 little lines underneath the 100. I put a 50 on one side, I put a 2 on the other, and I circle the 2 because the 2 is prime. And now I just need to focus on the 50. Well, that's equal to 25 times 2. And so underneath the 50, I write my 2 little lines, I put a 25 on one side, a 2 on the other, and I circle the 2. And now I see that all I'm really left to work on is the 25. And 25 is 5 times 5. So I write my 2 little lines, I put a 5 on one side, a 5 on the other, and those 5's are both prime, so I circle them, and now I look at my tree and I realize that all the bottom pieces, if you will, of the work are circled. And that means that I'm done with my work. I now can write down the prime factorization of 1100. It's equal to 2 times 2 times 5 times 5 times 11, which I really suggest we put in this exponential notation because it's in a more compact form then, and it would be written as 2 to the second power times 5 to the second power times 11, which is the same as 2 to the second, or 2 to the 2 times 5 to the 2 times 11 to the 1. Now, to be honest, were you a bit nervous when you saw that number 1100 in this example? It might have felt a bit large at first, but as long as you just chip away at these things a little bit at a time, you'll be fine. The process of building these factor trees is just a whittling process, and you can really handle very large numbers very easily with that sort of thing. Now, let's use these prime factorizations to our benefit by looking at another number theory concept. Here's the next definition I wanted you to look at. The greatest common divisor of two different numbers is the largest divisor that divides both of the numbers that you've been handed. Now, I think an example would help us understand what's happening here. So let's look at a quick example so I can explain the concept with some numbers in mind. I want us to find the greatest common divisor of 12 and 20. And by the way, lots of math books will call the greatest common divisor GCD as an abbreviation. So when they ask for the GCD of 12 and 20, they're asking for the greatest common divisor of 12 and 20. Now, the idea here is the following. We want to divide the largest number, we want to find the largest number which divides both 12 and 20. The most basic way to find this largest number, which is a divisor of both 12 and 20, is to write down all of the divisors of 12 and all of the divisors of 20, and then to find the largest one that's in both lists. So let's do that here. Let's write down all the divisors of 12 first. Well, they're going to be 1, 2, 3, 4, 6, and 12. No problem. Now, what are the divisors of 20? Well, they are 1, 2, 4, 5, 10, and 20. And now I ask you this question. What is the largest number that appears in both of those lists? Well, the answer is the number 4. And that means that the greatest common divisor of 12 and 20 is equal to 4. And again, let me explain what that 4 is. It is the greatest or largest number which is a common divisor of both 12 and 20. Now, that was a nice small example, but what if we needed to find something like the greatest common divisor of 1,200 and 2,520? Well, that would be a real pain if what we had to do was write down all of the divisors of 1,200 and then all of the divisors of 2,520 and then find the largest number that appears in both lists. That would really take a long time. And honestly, we would probably be prone to errors because we might miss a divisor in one or both of the lists. So let me show you a different way to find greatest common divisors, which actually relies on the fundamental theorem of arithmetic. Let's do a smaller example first, just so you see how things work, and then you can imagine how it would work for larger numbers. Let's find the greatest common divisor of 40 and 75. Okay, I'm going to go ahead and do this problem by writing down the lists of divisors, just so we can find the answer quickly. But then I'm going to show you the different way of doing the problem. The divisors of 40 are 1, 2, 4, 5, 8, 10, 20, and 40. Now, I hope you see that even with just a number like 40, writing down all the divisors can be kind of tough. Well, let's keep going. The divisors of 75, that was the other number in question, are 1, 3, 5, 15, 25, and 75. So the greatest common divisor of 40 and 75 is going to be the largest number that appeared in both of those lists. And that answer is 5. Okay, but even now, these numbers are getting big enough that finding all those divisors really is a bit annoying. So let me show you a different way to find that answer of 5, but I want to do so by using the prime factorizations of 40 and 75. So let's now look at 40 and 75 and write down those prime factorizations. Well, it's exactly what we were doing a moment ago. If you build the factor trees for each of these numbers, here's what you're going to find. 40 is equal to 2 to the 3 times 5, and 75 is equal to 3 times 5 squared. Now, if you don't mind, I'm going to write in those exponents of 1 where they belong. And that means we have 40 equals 2 to the 3 times 5 to the 1, and 75 equals 3 to the 1 times 5 squared. Now, once you have those prime factorizations in hand, and it would take a few moments to do that on a piece of scratch paper to build those factor trees, once you have them, though, you can quickly find the greatest common divisor of 40 and 75. Here's the general fact you need to know to find that GCD. To calculate the greatest common divisor of two numbers, you just look at the common prime powers in both of their factorizations, and you keep the one which is raised to the smaller value in each case. Now, rather than trying to say that in big theoretical terms, let me just go back and look at these two prime factorizations and walk you through it in this example. 40 equals 2 to the 3 times 5 to the 1, and 75 equals 3 to the 1 times 5 to the 2. Okay, I see in that 40 that it has a power of 2 in its prime factorization, but the 75 has no power of 2 in it. And so in this case, to find the GCD, I can ignore that power of 2 as I'm doing my work. Okay? Next, I see that the 75 has a power of 3 in its prime factorization, but the 40 is missing powers of 3. It has no power of 3 in the prime factorization of 40, and so I can also ignore that power of 3 that's inside the 75. Next, I see that there is a power of 5 in both the prime factorization for 40 and the prime factorization for 75. And that means that we definitely need to keep some power of 5 for my greatest common divisor. But which power is the one that I keep? Well, the answer is I keep the one which has the smaller exponent. Now, one of them has a 5 to the 1, and the other prime factorization has a 5 to the 2. So I need to keep the one with the smaller exponent, which is the 5 to the 1. And folks, that's all the prime powers that we have in each of these two numbers. One of the numbers had some 2's in it, one of them had some 3's in it, both of them had 5's, and that was it. So that tells me that the greatest common divisor of 40 and 75 is simply 5 to the 1, which is just 5. But that's exactly what we found when we wrote down those two lists of divisors and looked for the largest common divisor. So here I've shown you a way using prime factorizations to quickly find the greatest common divisor without ever having to write down those lists of divisors. Okay, let's try another example of calculating a GCD using this idea of the prime factorizations. In fact, let's go back to that example I showed you just a moment ago with slightly larger numbers. Let's find the greatest common divisor of 1,200 and 2,520. Well, the first thing we have to do is find these two numbers' prime factorizations. So in order to do that, you might want to go ahead and pause the lesson at this time and calculate those prime factorizations using some factor trees. Once you've done that, let's come back together and we'll finish the problem. All right, so the prime factorization of 1,200 is the same as 2 to the 4 times 3 to the 1 times 5 to the 2. And the prime factorization of 2,520 equals 2 to the 3 times 3 to the 2 times 5 to the 1 times 7 to the 1. All right, honestly, that was really the hard part of the problem. Now, finding this GCD is actually just a matter of reading off the prime powers correctly from those two prime factorizations. I first see that both numbers have a power of 2 in their prime factorizations. One is a 2 to the 4, and the other is a 2 to the 3. We keep the smaller of those two powers, which is the 2 to the 3. So the GCD will definitely have a 2 to the 3, or 2 cubed, in it. Next, there are also some powers of 3 in both prime factorizations. We keep the smaller one, which in this case is the 3 to the 1. Similarly, we're going to keep a 5 to the 1 for the GCD, since we have a 5 to the 1 and a 5 to the 2 in the prime factorizations. And lastly, one of the numbers has a power of 7 in it, but the other one does not. And so I'm going to completely ignore that power of 7. And that means that the greatest common divisor of 1,200 and 2,520 is exactly 2 to the 3 times 3 to the 1 times 5 to the 1, which is the same as 8 times 3 times 5, which is 24 times 5, which equals 120. So the largest number that divides both 1,200 and 2,520 is exactly 120. And I never had to write down either of the divisor lists for those two large numbers to begin with. I would have found that really annoying to have to do that. I think this way of doing this problem is really nice. Now, I can hear some of you saying, okay, yeah, that was nice, but gosh, can I use any of this for something helpful? Well, it turns out that you can. Remember when we were adding fractions a long time ago, several lessons ago? One of the things we must do when adding fractions with different denominators is to find the least common denominator before we add the fractions. Believe it or not, what we were just doing with GCDs can help us tremendously when the denominators of our fractions are big but different. So let me show you an example. I want us to find the common denominator that's needed to add 5/12 plus 3 over 20. Okay, what we need is the least common denominator for a 12 and a 20. Believe it or not, that number is easy to find because it's going to equal the following amount. The least common denominator there is going to be the 12 times the 20, all divided by the greatest common divisor of 12 and 20. So we're going to build this fraction with the two denominators on top multiplied together, divided by the GCD of 12 and 20. And that ratio is going to tell me what my common denominator needs to be. Now, the GCD of 12 and 20 is equal to 4. We found that a few moments ago. And so this fraction that I'm staring at is really equal to 12 times 20 over 4. And we can calculate this with no trouble. 12 times 20 is equal to 240. So this is just 12 times 20 over 4, or 240 over 4, and that's equal to 60 if you just do a little long division. And so we now know that we have to convert 5 over 12 to a fraction with a denominator of 60, and 3 over 20 as a fraction with a denominator over 60. Once we do that, we can actually add those two fractions. All I wanted to do with that example was to show you how to find that least common denominator. So I'm not going to do the actual addition. But notice here how doing the GCD of the original denominators tells me how to find what the least common denominator is going to be. Now, by the way, I should quickly point out that when I simplified 12 times 20 over 4, we had to deal with a somewhat unenjoyable multiplication problem before we divided by that 4. I did that on purpose because the order of operations tells us to work left to right with multiplications and divisions. But it turns out that in that problem, we could have done the division first and then the multiplication. And then we would have had 12 times 20 over 4 is the same as 12 times 5, which is 60. So we can get the same answer without the numbers being too big. Of course, anytime you break the rules like I just did with those order of operations, you need to make sure you're not messing up the numbers in the process. Now, let's do one more example of finding a least common denominator, just so we can see how we use these GCDs. Find the least common denominator needed to complete the problem 1 over 40 plus 1 over 75. Go ahead and pause the video if you'd like and try to solve this on your own, and then we'll meet back up together. Okay, as with the earlier example, this least common denominator is going to equal 40 times 75 divided by the GCD of 40 and 75. And we found a few minutes ago that the GCD of 40 and 75 is equal to 5. So the least common denominator is going to be 40 times 75 divided by 5. Now, we just need to calculate this amount. And we can use our skill in long multiplication of integers to see that 40 times 75 equals 3,000. And so 40 times 75 over 5 is 3,000 over 5. And that's equal to 600. And that means that the denominator we would need if we were converting 1 over 40 and 1 over 75 so that they had common denominators would have to be a 600. That would be the smallest denominator that we could use to finish that addition problem. Now, in this lesson, we've spent some time talking about some very important number theory ideas: prime numbers, prime factorizations, factor trees, and greatest common divisors. I hope you've enjoyed these topics. We'll talk more about some number theory ideas in our next lesson.